Hi, this is Anita, and we are dealing with kdtrees now. So the viewers of this video would have known about insertion and finding a minimum in kdtree. With this assumption, this video talks about how to delete the data from a kdtree. So in this example, we'll take a two-dimensional tree and we'll explore how deletion takes place. So this is the algorithm that we use for deleting the keys from the kdtree. So let us explore how does this algorithm works with such a tree. Let us go for some simple case of deletion. Before getting into that, I should recollect what are the steps involved in deleting a node in kdtree. As we know that kdtree resembles the structure of a binary search tree. Insertion too takes place as in the binary search tree. However, there are some modifications in the deletion. One is whenever you want to delete a leaf, then it is okay, you can delete it without any replacement of that node. But if you attempt to delete a node which is not a leaf, then you have to look for two cases. One is the very first attempt when deleting a node which is not a leaf is you have to look for the right child. If you have a right child, go to the right subtree, that is a right subtree, it's not a right child, right subtree, just jump to the right subtree and traverse to find the minimum in that right subtree. If you find such element, just replace the node to be deleted with this data and just delete the minimum data key, right? If you don't have a right subtree, then jump to the left subtree and find the minimum in the left subtree. Also do the same copying of data, but after copying the data, you have to move all the subtrees in its left towards its right. So I have summarized the operations involved in the kdtree. Let us uh, explore more with some examples so that you have a good understanding, right? So at very first step, I'll try deleting a leaf. For example, this is 2050. Okay. So on any deletion, it's going to start from the root. So my point would be 2050. So my algorithm delete has three parameters. Point x is the data that I wish to delete. So for example, here it will be 2050 and I'll be calling this algorithm with root node and the current dimension would be the dimension of the root node, that is 0. So initially my calling of this algorithm would be delete. The point is 2050, so I have to delete 2050. Then you start from root, then the dimension is 0, that is x dimension. Okay, as we do have only two dimensions, we are going to toggle between these two. So when I call the algorithm in this way, the root would be searched for 2050. The 2050 is not found here, so the x is not equal to data. So I'll move to this else position and will find x of the current position, whether it is less than the data. That is, I'm searching for 20, but the current x value is 30. So my node should be situated in the left. So I'm just making a jump towards the left. So I'll come here now 2040. Again the same operation delete will be called with the same key 2050 but with the left of the root node. So let me number this as A, name these nodes as B, C, D, E, F, G and H. So initially this will be called with root, now it will be called with B with the dimension of 1, right? So now it will be compared with B and it is not equal, however I have to look into the data. So it is not equal, so I will be looking it here in this dimension whether that x is less than or equal to this data. So I am searching for 50, but now I am encountering 40. So it must be in the right. So now my next calling statement would be deleting what node that I am trying to delete, 20, 50, and what node that I have reached now is C and with the dimension 0. See, the dimensions get toggled each and every time you call the delete. So now that C node will be checked. If t equal to null, no, it's not equal to null. So I'll be checking whether the data is the same or what I'm searching for. Yes, it is same. So it will be looking for its right. It is null. So it will skip all these statements, and it will looking for the left. So it is also null. So it will skip all these statements and directly comes to t equal to null. So it will automatically moves to t equal to null. So your final tree would be 30, 40, 20, 40 without this leaf, right? So this is a simple case. I hope it is clear to you. We'll explore the second case now. So I'm trying to delete this 30, 20 from this tree, right? So as usual, the calling will be done with delete 30, 20, so that this is the key that is going to be deleted, and it starts with root and with the dimension 0. So once again I'll name this as A, B, C, D, this is E now, F and G. So that I started from root, that is A, and now I am searching for 30, 20, it is not found here. So as the dimension is 0, it checks for 30. Both of these are equal, hence the data that I am searching for would be in the right. Okay. So now I will be making again a delete call with the key to be deleted and with C and with the dimension 1. Right. So this is where you will be finding out 30, 20. So now I find the key to be deleted at this position. So I have found the key at the position. So now my this is my CD and this is my next CD. So my current CD is 1 and so my next CD would be 0 at this position, right? So I'll be checking with the x data, x equal to data now. Yes, right. So this is x and this is my t. So both the data are equal. Hence I'll be checking for the right component first. So do I have a right for C? Yes, I do have a right node for C. So I have to find the minimum element from the right subtree. So I am going to move to the right. So this is going to be the right. So now this is T, right? And this is T's right. So I am jumping into T's right with the CD and the next CD. Okay. So I am going to find the minimum with this dimension. As this position is in the y dimension, I am going to find a minimum value in the y dimension only. So I am going with the minimum values. I am jumping into the right and I am looking for, as this is an x dimension, I am searching for y dimension, right? So I have to make the search in both the directions, right? So from this direction I get nothing, but from this direction I get 40, 20. So I'll get 40, 20 from the right and I don't have anything in the left. So I have two values to compare. One is 30, 30, another one is 40, 20. In these two elements, which element has the lesser value? I need to find the lesser value. Okay. So for y dimension, this 40, 20 has the lesser value, right? So when finding the minimum in the right subtree, I find 40, 20 as the minimum. Okay, this find minimum is the crucial method that has to be understood very well. So when I am searching for the right subtree, it returns two things. One is 40, 20 and as well as the root. So I am finding the minimum out of these two based on the y dimension. So I am taking 20. So this is going to be the minimum. So what should I do with that minimum? I am finding that minimum and replacing this data into T's data. So where is T? This is T. So I am replacing this data into here. So this 3020 now will become 4020, right? And now once again I am trying to delete this t is right. So now I am going to delete this t data starting from this position. So what is my data now? It is 4020. So as I have copied down to this in this position, I need to delete that 4020 which is found somewhere down in this tree. So I am doing the same thing of deleting 4020. Okay, please understand, we have deleted 3020 already, we have simply replaced. Now we should delete 4020. So I am searching for 4020 from this position. So this is not found here, but 4020 is found here, and actually it is a leaf. So deleting a leaf is very much easier. So this is going to be the final result of your tree when I try to delete this 3020. So this is the resultant tree after replacing 4020 and deleting the actual 4020. Hope you understand this case where you have a right child. Okay. So let us now explore another possibility where you don't have a right child. So let us choose this node so that we'll explore the way how it is getting deleted because it does not has a right child. So shall we start exploring this deletion? Okay. So as we know, the deletion starts from the key what we want to delete. So we want to delete 2040. We start from the root. The root is actually, we name it as 0 and we started with the current dimension as 0. Right? Fine. So it will search for 2040 here. It is not found actually. So it will look for X dimension 30 and 20. So 20 would be automatically in the left side. So it will make the same deletion call with 2040 the key and with V and with dimension 1. Okay. So now it again comes here to the B, the node B. Then the keys are equal and it is in the dimension 1. So my CD will be now, current dimension is 1. My next dimension is going to be 0. Okay. So now I am here in the algorithm. So I have found a match. So I am looking it for the right side. So T is right, I am looking, it is null actually. So I am skipping all these statements and coming to here. T is left is not equal to null. Yes, it is not equal to null. We have some left subtree, right? So I am jumping into the left. So now this is the node to be deleted. This is T and I am jumping to T's left. So this is T's left, right? So 1020 I am jumping here and then I am finding it a minimum value from this set in the same dimension. What is the dimension? Y, because my deleted node is in Y dimension. So I am going to search a lesser value for the same dimension. Okay. So T is left, I have 1020, it is an X dimension. So I have to make the search in all the directions. So when I look into, I have 1020 and I have 1030 also. So when looking into that, I am finding that 1020 is going to be the minimum. See, from this side I will get a null and from this side I get a value of 1030. But among these three values, this is null and this is 1030 and this is 1020. Among these three values, I find the lesser y value only in this. So my find minimum is 10, 20. Okay. Now I should replace this 10, 20 here. Okay. So instead of 30, 40, I am getting 10, 20 here. Okay. Right. So this is actual T. So T's data is copied, but you have an actual 1020 here and actual 1030 also here. Okay, just a copying is done with this first statement. So I have to delete actually the 1020 from the left subtree, right? So I'm coming into this left subtree and I'm trying to delete this data. So I'm repeating the same procedure. How do I delete this 10, 20? Again, I find a right child whose value is minimum. So I am coming to the side right child as well as see 10, 20 is in x dimension, right? So I am finding it a minimum tree here, but I could not find I could find only the same value. Okay, so I have a child here. So my value is 10 comma 30. Okay, so this 10 comma 30 will be copied here, right? So 10 comma 30 will be copied here, and again the same deletion is done with 10 comma 30. Now 10 comma 30 is a child, so it is now destroyed. So actually our key, and after that you need to have a very important point. This is t's left, right? Originally this is t's left. Now whatever change you make in the t's left must be stored in the t's right. That is a very important thing that you need to do. So in this algorithm you may be finding a change in the second statement. Whatever you delete in the t's left must be immediately transferred to the t's right. So what change am I putting here? Instead of this tree, I am converting into this tree. So this changes to the gets moved to the right subtree. So now all my left is now transferred to the t's right. So 10 comma 30 will be the new position. That's fine. So what are we are looking into? We have moved this 10 comma 20 to this position, and we have adjusted this tree. So we are trying to delete 10 comma 20 here. So in order to find 10 comma 20, I am going to find a minimum in the right. So I do have only 10 comma 30. So I am replacing 10 comma 20 with this 10 comma 30, and again I am deleting this 10 comma 30 leaf. So now my tree would be like this, and I am changing all the left into my right. So after completion my tree would be 30 comma 10 with its left child as 10 comma 10, and as usual you have all of your other keys in the right. So this is how the deletion is being done. So please practice deleting 40 comma 20 and try adding more data points so that you could understand you could have a clear picture of the KD trees. This is another example for showing you how the deletion works. See, this is an example of a tree in which we try to delete this 30, 40. So as per our rule, we are going to search for the minimum element. So we are going to, here I have 30, 40. So I am jumping to my right as I have a right pointer. And from here, I am trying to find the minimum element. Okay. So when I try to find the minimum, so this is y dimension. So I am simply searching it for in both the directions. But as of now, I don't have both the directions. So I am simply putting it up 50, 30. Okay. Now again, I am trying for getting my minimum y. Right. So I find my minimum y as 35 comma 45. Since right child is not null and the dimension node is x, we find the node with the minimum x value in the right child. Okay, I hope you understand. So we are going to delete a node in the dimension x. So I am going to search a minimum value only in the x direction. Okay, so when I am coming to this 70, 70, it is actually in the y dimension. Okay, so if it is y dimension, I am going to extend my search in the both the directions. So here I don't have a right child to traverse, so hence I am looking into the left subtree. Now it is actually in the x position, so I am just jumping into the left position only. And here it is in y direction, so I need to jump to both of them, but I don't have anything, so I will be returning this 35 and 45. So as of now, this point is going to be the minimum point in the x dimension. So what should I do? I have found the minimum element, so I should just copy that in this 30, 40. So I have copied, and actually I have to delete this 35, 45 from this row, because when I copy this 35 to 45 to this place, I have 35, 45 in two places. One here and another one is here. So I actually should delete this 35, 45 from this tree, right? So I'll be searching again 35, 45 from this position. So I'm finding here this is a leaf, hence a simple deletion would do, resulting in this tree. Okay. So now we shall explore another case. From this node, I am trying to delete this 70, 70. Okay. The dimension of 70, 70 is y. But actually the search starts from x dimension 30, 40. So it will jump to this one and it finds 70, 70 but in the dimension y. So I have to find a minimum element only in that dimension. So first I look for my right child. I don't have a right child here. Okay. So I'll move for my left. So I'll jump to the left and I'll try to find the minimum value for y dimension. So as this is x dimension, I'll be looking in both the subtrees. I don't have a right subtree here, hence I am looking into only my left. Okay. So here I have an y. Okay. So at this juncture, I don't get anything from the right child, but I get a 35, 45 from the left subtree, and I have a value of 50, 30 in my root. So I have to compare these three elements. One has 45 as y, another has 30, and one has null. So among this 45 and 30, I choose 50, 30 because this possesses the lowest y value. Please understand, finding minimum will not return just 45. It will check all the possibilities and will return 30. So now 50, 30 is the child that is to be replaced. So I have to copy this 50, 30 here. Okay. And after copying, I have to delete this 50, 30 from this location, right? So when I try to delete this 50, 30, then only child that is going to be replaced is 35, 45. 50, 30 is in x dimension. So I will be making my search as usual and finding that 35, 45 is going to be the replaced. So instead of 50, 30, 35, 45 will be put up here. Okay, please understand 50, 30 is originally copied here and 35, 45 also copied here. Then 35, 45 will be deleted. After deleting, we should be swapping this left subtree to the right subtree. This is a really needed one. As we are searching in all the directions, this is really needed one. If I am trying to take from my left subtree, I have to swap. Okay, so please understand this has to take place. Okay, so after swapping, our tree changes into, because this is 50, 30 and this is 35, 45. So now 35, 45 changes to the right of 50, 30. Okay, so these cases may make you understand your B tree well. Thank you for listening. Insertion and deletion. Thank you for watching.